Oops, what was that? Yeah, you're good. Okay, hey, thank you, Brandon. Okay, let's go ahead and get moving then. Um, First off, I polled my other 141 class Wednesday evening. I have two people that are working in healthcare. They're experiencing some really difficult times. One person, they're only letting them have one mask to use the whole day, and the other person, she's not working now because she had a couple people in her family test positive. So a lot could have happened since the last time we were together. So if anybody feels like say something, uh, get a hug or whatever, you've got it right now. So just chat it or you can say it, whichever you want to do.
To piggyback on that, what you said,
Sure.
um, my god sister, she works at a hospital in the suburbs.
Yeah.
And she was saying, basically like the same thing that you're saying that, well, she works in the cardiac unit, so she was saying that they really don't have any cardiac patients. So since like a lot of people are coming into the hospital and like getting tested and like so like their overflow of like the ER is going to her unit. And
Oh,
so she was saying that one of her coworkers actually had a patient who tested positive. So she said that so she said she was getting called by like the Illinois Health Department to make sure she's doing good, but they're really not doing much for them. As in the sense if like you're taking care of somebody who tested positive, you still have to work. You just have to take like more precautions,
right,
so to
right.
say.
Yeah, yeah. That's going to be tough for a lot of our family and friends. So thanks for sharing. Okay, anybody else before we move on to other things? Okay, I'm not going to turn my camera on today because I think my connection's just barely making it. So I'll get that worked out before Monday. So I hope. Anyway, okay, what we'll do now is take a look at Blackboard and see what's doing there. Okay, um, so looking at Blackboard, just a reminder, we're going to have exam 3 on Wednesday. What you will do, I'll mention this again on Monday, but what you'll do is go ahead and come in to collaborate on Wednesday, and then I'll activate a link back in Blackboard. You'll click back on Blackboard and go to that link. It'll take you to Sapling. The exam will be in Sapling. It'll take you to the right place in Sapling, and then you'll do it there. The questions, everybody's going to be getting them in a different order, and the answers will be uh, random for each person. So, I'm not going to worry further than that. If people want to, whatever, we'll go with it like that. And you'll be able to see, once you submit your answers, you'll be able to see which questions you got right and which questions you didn't get right. The exam will be just like what we had on our previous two exams, 5 choices. Questions will be similar. And you just look at this announcement here to see, it's chapter 13 and then a little bit of the previous stuff. So I guess before I go on, does anybody have a question or anything about the exam? Yes, Brandon, go for it.
Do you know how many questions the exam is going to be? And is there like a time limit that we have to like take the
Uh,
exam?
Not really. It'll be similar to what we did, with the previous two exams. Some people will get done early. They'll just have to chill until everyone else gets done. Um, I'm not gonna cut anybody off on it. So, uh, so if it takes the full 2 hours, that's or hour and 50 minutes, that's okay.
Okay, thank you.
Alrighty. And as far as the number of questions, I can't look at it right at the moment without you guys seeing the exam, so I really don't have a good way to do it. I think it's 27, but I could be wrong, so I don't know for sure. If I get an opportunity to look at it a little bit later in our session today, I'll come back with a number. Anybody else about the exam? Okay. Then the recordings of our Collaborate sessions are available. Right now, you can just go to course materials, and then this link right here, the second one that says Collaborate recordings, is currently going to be able to take you to the March 30th class. I failed you and forgot to record on Wednesday. I'm sorry. So it's not there. There's no way to go back to Wednesday. But anyway, what we're going to have to do moving forward, though, is I'm going to put all of these in this folder right below where you come into the room at. So you'll be able to click there. And right now, all I've got there is the transcription of the chat. So you could click that, and this is, Noah saying, "What's good, y'all?" Stuff like that. So anyway, that'll be available, but then also the video, there'll be a video link here, and it'll take you to YouTube. The reason being that we do not have enough space in Blackboard to hold all of the recordings. So we have to download them from Blackboard to our computers, and then I have to upload it into YouTube. And then there'll be a YouTube link. So that's the way it'll be going forward. In the middle of trying to do that, and let's see, it's 99% processed. So anyhow, I'm getting there. Okay, that's it on announcements. Going to task. The only two things that are that are coming up, of course, is our exam on April 8th. I don't have the sapling assignments in here yet. I'm going to go ahead and be doing that soon and try to catch up on having those appear here. But right now they're not. And then the final exam is here. And then don't forget, you have a lab report due on Monday from what we did on Monday. And let's see, is there anything else? I don't think so. I believe we're good on anything new. So does anybody have a question on any of that stuff? Maritza, I have to ask you, what is that picture supposed to be? I don't get it. Your on your profile.
Like humor. So it's supposed to be the coronavirus. But so it's a long story. So like the little girl, she's
Yeah.
actually like a meme.
Uh,
She was recorded and she was making like those faces to people, and so it became like a big thing. And so
uh,
yeah.
okay. Well, I tell you what, I got something that I'm gonna have to hang up and share it. Some guy has redone the really old song Miss America Pie and made it into talking about our lives now and how things have changed. It's actually pretty good. The guy can actually did it correctly. So I'll probably put that up there eventually. But anyhow, I got to stick with the more critical stuff right now. All right. So with all that done, we'll go ahead. Hey, Keon, what's up? Sapling homework. Oops. The only problem when these things pop up in chat is they're only there for a second. Can get pushed back a day. Can we push it back a day? Just one more day. Yeah, I can do that. But since you said it, I need to go do it right this moment or I won't remember it. So hang on a second. I'll have to log into Sapling. Oops. I see somebody said something. Okay. So that was specifically the 14B homework, not a topic introduction. Okay, good. I'm getting there right now. Okay, 14B homework is now going to be Sunday, the 5th. Okay, so that's changed. Yay. Okay, so we did that. So now let's go on and we'll take up on lecture where we left off. According to my understanding, I'm not generous, man. Don't say that. If I was generous, I'd be making face masks for everybody and staying up all night. Okay. Nope, that's not it. Oops. Okay, we were in chapter 14, part B. Looks like about slide number 6. So let's get that going. Oh. Hang on a second there. Let me take a look at what you're saying. Yeah, okay, so that's where we left off. Now, I'm looking back to that. Topic introduction, number 12 is still on 0 points. Yes. Okay, you know what I'm gonna ask you to do? Send it one more time to stuff going on since when you did that, and so I did not remember it. So if you would please, thank you very much. Just email that to me one more time, okay? Alrighty, so here we are. But of course, oh, I guess that means of course you're gonna send me another email. Okay. Anyway, we left off here at the Henderson-Hasselbalch equation, where we were able to calculate the pH for a solution by okay. I'm going to be a little slow for a while here. I've got a new trackpad, which I haven't quite got it all worked out. But anyway, we have this equation now, and this is a quicker way to get the pH when you know the Ka and you know the amount of an acid and the amount of its conjugate base. It's quicker than doing a rice table, so that's why we're doing that now. Okay, so then this is an example of using Henderson-Hasselbalch equation. So they're asking us, what's the pH of a buffer solution if it's 0.12 molar for lactic acid, so that's our HA, and 0.10 molar sodium lactate, that is our A negative. And what we're going to see later on is, since both of these are in the same solution, we can use either molarity or we can use moles, and it won't matter. You'll still get the right answer. You know, I don't know if this trackpad was worth it. Maybe it was, but anyway. They gave us the Ka for lactic acid here, but we're going to need the pKa in order to do this. So we're going to need to know pKa. So we would have to then, to get the pKa, of course, that's going to be the negative log of the Ka. So you're going to take the log of the Ka, then change the sign. And if you do that, then you get this number right here, 1.4 times 10 to the negative 4. And then these other two values over here and here, those come from the information that was given. So we said that our HA is 0.12, so that's where this comes from. And our A negative is 0.1, and that's where that comes from. Then to get our final result, the 3.85, to get our final answer, the 3.77, we take the 3.85, which is the pKa that would have come from here, and we would have taken the log of the fraction, gotten that value, and then our final answer would be right here. Okay, what is going on here? Oh, there we go. So then, sorry. So then, what we want to go to from there is what happens if you add a strong acid or a strong base to a buffer. We did this back in a simulation lab right before, the zombie apocalypse started. And the approach to that is two steps. First one is that you treat the addition of the strong acid or strong base as a neutralization reaction, where it says all of the added base reacts. So if you added acid, it all reacts. If you added base, it all reacts. And then it's going to alter the amount of the weak acid and its conjugate base in your buffer. You would then use the Henderson-Hasselbalch equation to calculate the pH. We've got a flowchart that illustrates doing this. So it says here, you have a buffer that contains a weak acid, HA, conjugate base, A negative. Now, if we ignore these two for right now and just go over here and solve using Henderson-Hasselbalch equation, we could get the pH for the buffer before we have done any additions. But then if we come along and say we add a strong acid right there, then it's going to alter the amount of the A negative and the HA. So this H plus here, that could come from something like hydrochloric acid. So the hydrochloric acid that we put in is where the H plus comes from. It would then take the amount of the A negative that we have in our buffer, and it would convert some of that into HA. We'd then take the new values of HA our weak acid, and its conjugate base, use the Henderson-Hasselbalch equation, get the pH. Or if instead of adding a strong acid, we add a strong base, it's going to react like what we have up here. Strong base, for example, sodium hydroxide. The hydroxide would then react with the weak acid that's in our buffer, and it would make more A negative. So we decrease the HA, we would increase the A negative. We take the new values of HA and A negative over to Henderson-Hasselbalch equation and calculate the pH again. And what we should be looking for when we're doing these is, in the first case, if we're adding a strong acid up here, that should lower the pH some, because this acid, acids have a smaller pH value than neutral, so it should lower the pH when we calculate it. If, on the other hand, we add the strong base, that's going to decrease, that's going to increase the pH, because it's a base, and bases have higher pH numbers. So when you do the Henderson-Hasselbalch equation, you should see the pH increasing. So you need to check your answer when you get to the point out here where you've solved for the pH to see if it actually is going in the direction you expect. Our next slide is going to take us to an example of that. So you start out, you got a buffer that's 0.3 moles of acetic acid. So this is our HA. And it's 0.3 moles of sodium acetate. So that's our A negative. So if we stopped at this point, we could just get the pH of that buffer. And they're both in 1 liter of water, which means that if we take these and divide them by 1, not only would that be the moles of the HA and the A negative, but it would also be the molarity of the HA and the conjugate base, the A negative. But what we're going to see is that since they're both in the same volume of solution, you don't have to convert them to molarity. You can just use them as moles. We'll see that in the next slide. Then what we're asked to actually do here is to see what happens after we add 0.02 moles of a strong base, sodium hydroxide. They're telling us that the pKa for acetic acid is 4.74. So we're going to use that in the Henderson-Hasselbalch equation eventually. Now what's happening when we add the strong base is in this box over here. The HA, or the acetic acid, is going to react with the sodium hydroxide, and it's going to make more of the acetate, or the A negative. It's a neutralization reaction. So you're also getting water, but it doesn't matter. And so what will happen here is the HA is going to decrease from what it was over here. The 0.3 is going to decrease, and the A negative is going to, excuse me, the A negative is going to increase. There's a bad looking arrow there. We get a note here that if instead of putting in a strong acid, wait a minute, if instead of putting in a strong base, we put in a strong acid, you're going to get the opposite effect. You're going to increase the HA, you're going to decrease the A negative. Now this table that we see here is not a rice table. It's just a way of keeping track of what's going on in the neutralization. So we put in here the amount of the HA which was up here. We put in the amount of the base that were added. So that's going here. And then we put in the amount of the A negative, or the conjugate base. And this is getting a little messy, but anyway, it goes there. See how things change. Well, the strong base is totally consumed so that you end up with 0. That's what happens when you use either a strong acid or a strong base. They're going to be totally consumed. Then we're going to use up the acid like we see over here, that the hydroxide is going to neutralize the weak acid. And then we're going to increase the conjugate base, which is over here in that process. So that at the end, the amount of the HA is now 0.28. The amount of the A negative is now 3.2. Going to the next slide, we're going to put those into Henderson-Hasselbalch equation. So in the previous slide, it was given that the pKa was 4.74. And then in our table, we saw that the amount of the HA is 0.28, and the amount of the conjugate base, the A negative, is 0.320. We take the fraction and we do the log of it, and then we combine that with the 4.74, and the new pH of our solution is 4.8. So notice there that we added sodium hydroxide, strong base, and therefore our pH became bigger, which is what we would expect. We want to always check and see if that's what our result is. Okay? So now we're going to do a worksheet where we're going to calculate the pH of a buffer before we add anything, the pH after we add an acid, the pH after we add a base. Okay? So I'm going to kill this right here, the PowerPoint. Now, if you want to keep that PowerPoint in front of you, you can go back into Blackboard, go to the presentations, and you can open it up. So, you know, if you haven't done that, you might want to go ahead and have that in a separate tab on your browser so you can refer back to it. But I need to get rid of it now so we can look at our worksheet we're going to do. And I'd ask folks to print out the worksheets. I realize though that some people may not have a printer available to them right now. So instead, you could just write this on a piece of paper. So now I'm displaying the worksheet. And so what we've got here is it's 0.15 moles of propionic acid. So that's our HA. And then we've got 0.1, oops, we got why is it doing that? We got 0.1 moles of sodium propionate. They're both in 1.2 liters, but it doesn't matter. We can just use these two numbers since they're both in the same solution, same volume. You don't have to convert them into molarities. If you do, you'll still get the right answer, but it's just some additional steps. Now, don't go using this in other things that we've done previously, because that won't work. But in this case, we can do that. Now, this worksheet is missing an obvious piece of information that we need, and that is, what is the Ka of our our weak acid. So I need to get that for you guys so you will have that to look at. Okay. And the value is 1.3 10 to the negative 5. So it's 1.3 10 to the negative 5. What we're going to do then is I'm going to put you into groups like we did previously. And then I'll activate the groups. I need to assign a few people to groups. So this will take a second. So just bear with me, please. Okay, I think we're good to go. I'll go ahead and hit the start button. If you see you're in the wrong group, let me know.
Oh,
Wait a moment.
everybody phone?
Okay, where are you?
Again. Hi, folks. I just canned the group so you guys, all your open mics are there. Oh, I got a few.
Oh yeah, Ooh.
These silence your microphone so we don't have too much happening here. Thank you very much. Okay, we'll look at the key for that real quick.
Hmm. 4.7.
I told y'all.
Yes, here you go. This was that last one. Hang on a second here. Let me. Oh, well, we kind of went all over the place here. 4.9. Let me go back. 4.7. Oh, you're talking about the second one. Okay, I'm sorry. I missed. I intended the last one. Okay. Yeah, Noah. Anyway, okay. Does anybody want me to go over this first one, or is this clear to you guys? Raise your hand if you want me to go over the first one. Nope. Okay. So for this next one here, this is where we added our point. Whoops. Gotta get the marker going. Oh. Okay. We added 0.1 moles of sodium hydroxide. So that's this right here. The 0.15 from the acid was what we were told previously, and also the 1 moles for the conjugate base, the A negative. So then, since this is a base, it's going to decrease the acid. It's going to increase the conjugate base. We now have a couple of new numbers for HA and A negative. We then take the pKa that we calculated earlier, and then we put in the A negative here, we put in the HA here. Then after you take the log of the fraction, you get a negative 0.1047. Then you combine that with the 4.886 and you get to 4.78. Anybody got a question? Raise your hand, please. Okay. So now we'll look at this second one here, or third one. So now for this one, instead of putting in base, we put in acid. We do the table again. There's where we put in the acid. The 0.15 is what we had with the initial buffer. The 0.1 we had from the initial buffer. Putting in HCl is going to increase the acid and it's going to decrease the conjugate base. You got two new numbers. Those go into the Henderson-Hasselbalch equation. Still got the same value of the pKa. You take the log here. You get this number, negative 0.2499. Combine those together and your pH is 4.64. Has anybody got a question? Okay, looks like we're good there. So now let's get back on to the PowerPoint. And we'll skip down to the slide we were on. Or the last one. The last one was where, you know, we did this example. Oh boy, come on. There we are. No, that's too much. Okay, anyway, this was the example doing the same thing we just talked about. So then, now this gets us to something that you notice that when you add a strong acid, you're going to lower the pH. So when we put in, oops, let me get a marker going. when we added something like hydrochloric acid, the pH goes down. And then we add something like sodium hydroxide, the pH increases. Stop it. Yes, you can do that, Noah. Anyway, um, so so anyhow, that's what's going to happen to pH. The idea, though, of having a buffer is to minimize the. I ain't doing nothing. Yeah, I know you're not doing nothing. I know exactly who would do that. So I mean, it's like obvious. Let's see if I can do what I. You didn't do it? Okay. Well, anyway, I think I can select it and erase it. No, that don't work. Oh, yeah, I do. I can do that. Okay, it's all gone. So anyway, but it didn't change it very much on those two we calculate on. But eventually you can change the pH too much, and now whatever you're trying to control, goes out of control. Anyway, okay. So there's something called buffer. Oops, there's something called buffer capacities. Eventually, here we go. There's something called buffer capacity, which is how much can we alter the pH. Okay. Anyway, I'm going to ignore that. I'll figure out how to turn you guys off eventually. So anyway, that's when it becomes excessive, and they call it changing it to an appreciable degree. For our purposes, we'll say if the pH changes by plus or minus 1 pH unit. So if we start out, say we got a buffer that's 4.8, and we add an acid and it becomes, say, 3. Now we have changed it to an appreciable degree. We've exceeded the buffer capacity. Or if we add a base and it goes to 5, let's see, I think I actually did the other number wrong. It would actually be more like 3.7. Anyway, if we add a base and the pH went up to 5.9, we would say that it's changed to a appreciable degree and we've exceeded the buffer capacity. So anyway, the other piece of this is if we use the Henderson-Hasselbalch equation to see what the pH is going to be, like we just did, a 1 molar buffer solution is going to have a higher buffer capacity than a 0.1 molar because there's more weak acid conjugate base, or if we made it with a weak base, then a weak base and its conjugate acid to neutralize the solution. Okay? Anybody got a question on that idea? Raise your hand. Okay. We'll go to the next slide. So if we go back to, let's see, if we go back to this slide here, where we're trying to calculate what the pH is of a buffer solution. We did not have equal amounts of lactic acid and its conjugate base, sodium lactate. So that up there is the HA. This here is the. These two numbers are not the same. They're different from each other. What we're doing when we do something like that is we're altering the pH of the buffer. So you can produce a buffer with several different possible pH values depending on how much HA we have and how much A negative we have. But what the slide is getting at that we had just gone to I'll go back to that here. It doesn't work very well if we exceed those differences in the HA and the A negative. So it says if one concentration is more than 10 times the other, the buffering action is going to be poor. So that basically means that we're limited in the amount that we can change the pH. Usually it's plus or minus from the pKa. So let's say that we've got a pKa equal to 4.8. We could make a buffer that is 3.8, or we could make a buffer that's 5.8, depending on how much of the HA and the A negative that we have in the buffer. But we don't want to make those so different that you go less than 3.8 or more than 5.8. Okay, everybody got that one? Okay, we're about to switch topics here quite a bit. So I would say, has anybody got a question on any of this stuff we've done up to now? Okay, not seeing anything. So I'm going to go to the next slide. What we're going to be doing for the next couple slides is looking at titration curves. And the idea here is from the shape of the curve, from the shape of the curve, we need to be able to identify what kind of titration we're seeing. In this case, we're seeing a strong acid with a strong base. The way that we know it's a strong acid is because the pH starts at a value that's like 1 or less. The way that we know that it's a strong acid also is the curve is linear at the beginning. In other words, at this beginning part here of the curve, it's a straight line. It doesn't have a curve in it. Now we'll compare that to a weak acid in just a second. But what we want to do next is, what if it's a strong base being titrated with a strong acid? Well, first off, the pH is going to be something greater than 12. So you can see we're starting out at greater than 12. The other thing is that, again, it's this linear thing. This is a straight line here, this beginning section. Now we'll look at an example of where it's not a straight line. Now, here, this is a weak acid, and we're starting at a pH greater than 2. See right there, it's greater than 2. Also, it has a curve at the beginning. You see this curve right here. That would indicate that this is a weak acid instead of a strong acid. Otherwise, the titration curve looks the same as with the strong acid. So this part up here looks the same as for a strong acid. It's only the very beginning part that looks different. If this were a weak base instead of a weak acid, it would look the same. It'd just be flipped over. So it would start at the top and come down. It'd be curved, and the starting pH would not be up around 12. It'd be something less. And I got one more slide I need to show you. What we're seeing here is this first curve, the one right there that I'm pointing at, that's a strong acid. But the other ones, all these through here, these are weak acids. And notice that their starting pH is something greater than 1, and they have a curve. Now, this first one doesn't have much of a curve, but this one, you can definitely see that it's a curve. So if you saw pictures like these in the future, you want to be able to say that, hey, this curve is a strong acid with a strong base. That this curve is a strong base with a strong acid. This next curve, if I can get it to move, oh, there we go. This curve is going to be a weak acid with a strong base. And then, like I was talking about, it's going to look something like this. It's going to come down, it's going to have a curve, then it's going to come across, and then it's going to go down, and it's going to go over. Okay? So the curve is going to give it away that it's a weak base instead of a strong base. Has anybody got a question on identifying those? Yeah, no, what's up?
Where's the point where the pH corresponds to a solution of the weak acid?
Could you say that again, please? I don't think I'm following
It's a,
you.
it's a question on the homework. It's like
You're trying to get me to answer the homework. So sneaky. No. Go ahead and say it again, please.
there's 3 points. It's like the first one, it says the point where the pH corresponds to a solution of the weak acid in water.
Oh, well, that's the first. Well, that's the first where you put it in any base. So that's at the very, very beginning. So it'd be like right here.
And then it says the same thing but with a conjugate base.
Conjugate. Oh, okay. That's going to be. Let's see. That will be conjugate base. That's really the equivalence point. I'll tell you what. Why don't you send me the number of that question, okay? And I'll take a look at it, and I'll send out an email to everybody about it. Okay.
Okay.
Okay. All righty. So let's go to another slide. Okay. So here, you remember in 140 we did a titration with an indicator, and the idea of an indicator is if you don't have a pH meter and you're not monitoring the pH, you're not going to actually see this curve right here. It's not going to be there. Somebody needs to mute their mic, please. Thank you. Anyway, if we're doing a titration and we don't have a pH meter and we're not going to see that curve, we still need to know where the equivalence point is. And the way we do that is we have an indicator that changes color. It goes from, in this case, no color up to this purple color. So the indicator that we used in Chem 140 was phenolphthalein. But there's a reason why we picked phenolphthalein and not some other indicator. On the right side here, we've got an indicator, methyl red, and it changes color at a lower pH. So if you use this as your indicator of titration, you'd think the equivalence point is right about where I'm drawing, and it's not up here. And so you would underestimate the concentration of your acid. That just wouldn't work. Okay, so anyway, you have to pick the right indicator with the right pH at which it changes. And here is just, it shows a bunch of different indicators and the range of pH that they change at. So you can always find a indicator it's gonna fit. Okay, guys, hang on a second. I've got a text message from another student. Let's see what's going on. This is interesting. I have no idea what's going on. Okay. Okay, this is going to be the last slide off of this chapter, and Sometimes you can have an acid that has more than one hydrogen that is acidic. So this is phosphoric acid right here, H3PO3. All three of those hydrogens are acidic. Over here, we've got a picture of the phosphoric acid molecule, and it has 1, 2, 3 acidic protons. Now, in the picture below here, we're starting to titrate it. So as we're coming across, blah, 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 when we get to about right here, we have removed a proton. It's that one right there. We still have the other two. So what we just did, it would be represented in this equation where we took the H3PO3 and we made it into H2PO3, negative. It's got a negative charge now, lost a hydrogen. Down here, this summarizes how these things change. You lose one hydrogen, you gain one negative charge. Now, moving further up this plot, we now have H2PO3 negative is our acid, and its conjugate base is, when we get up to here, the conjugate base that we now have is HPO3 2 negative. And then if this curve could keep going up here somewhere, if that were possible, then we'd have another equivalence point, and that would be this last equation where you're starting with an acid that's HPO3 2 negative, and you lose that last hydrogen. Now it's PO3, or excuse me, it's PO3 3 negative. Now this won't, this part here, I'm gonna do that. The part that I was, oops, lost my marker. This part that I was drawing, it can't happen in a solution of water. We can't make it basic enough. So if you were doing this experiment, you would never see this part. You could just keep adding base and it would never occur, but you could get the first two. So you need to know, the question always, Professor, what do I have to know? Well, you need to be able to recognize what's the acid and what is the conjugate base given an equation. The same thing would apply down here and apply down here. So you need to be able to pick out what's the acid, what's the conjugate base, even when it's a polyprotic acid. Okay? Anybody got a question on any of this stuff? It looks like not. So we're going to go to our next chapter. Sorry, the wheel is just spinning. The whole world is going to completely collapse when the internet stops working. All right, let's try that differently. Okay, I'll try this in a different way. Okay, we can do it like that. But not thermo. Let's go here. And so now we are on chapter 15, equilibria of other reaction classes. So what we're going to be looking at here is some things besides acids and bases. By the way, I'm going to go back and see if my share is working. No, still not working. Okay, we can do this. So the way this chapter starts out, we're looking at a sparingly soluble compound. So we started out in Chem 140 saying that some things were just not soluble, and you memorized the solubility table so you could identify them. But what we have in this picture here, unfortunately, in this kind of presentation, it's not going to let me mark on these. I'm sorry, guys. So this chunk of stuff in the middle here, this is a sparingly soluble compound, and this could be something like silver chloride, so AgCl, and it's surrounded by a whole bunch of water molecules. Well, eventually some of the silvers and some of the chlorides are going to break off into solution, and when that happens, then it will dissolve some, but only a small amount, only about 10%. Now we can look at this for some other sparingly soluble compounds like barium sulfate or barium phosphate. So this equation here represents what happens with barium sulfate. It's going to produce Ba2 plus and SO4 2 negative, or the two ions. And we can have an equilibrium constant for that. But now notice that in the equilibrium constant, we don't have the barium sulfate in the denominator because it's a solid. Remember, we talked about heterogeneous equilibria like a couple chapters ago, and we said that if you have a solid in a solution of aqueous solution, that it does not appear in the equilibrium equation. And then we also said the same thing if you have a liquid, that we're not going to include it. So this is the formula for the equilibrium constant for things. Now these have a special name. They're called the solubility products. So that's why you see SP as a subscript on the K. Then below we got the same thing. This is with barium phosphate. So you've got 3 bariums and 2 phosphates. Remember to put the coefficients in. And get those from the equation of the ionic compound. So you got a subscript of 3, you got a coefficient of 3, you got a subscript of 2, you're going to have a coefficient of 2. Then to get the equilibrium constant formula, it's the concentration of the barium 2 plus. Since there's a coefficient of 3, it's going to have an exponent of 3, and since the coefficient over here for the phosphate is 2, it's going to have an exponent of 2. Let me see if this thing started working. Nope, it's not going to work. I want to check and see if anybody's got a question. So, okay, hopefully everybody's still with me. Oh, where did the coefficients come from again? Okay, let me show you. So the coefficients are coming from the formula for the ionic compound. So you see the barium has a subscript of 3. So when you write this out, it's going to have a coefficient of 3. And the phosphate has a subscript of 2. That's going to give you the coefficient of 2. Ah, good. So now we're going to take this a little bit further, and that is there's two ways to express solubility. Well, there's two related values. One is the solubility, and the other is the solubility product. The equilibrium constant, the KSP, the solubility product, is not the same as the solubility. The solubility is actually the quantity of the substance that dissolves to make a saturated solution. Saturated solution is the highest concentration solution you can possibly get from these. So solubility is a concentration. KSP is an equilibrium constant. They're different. Now for the solubility, we can express the concentration either the way we're used to, moles per liter or molarity, or you could do it as grams per liter. This flow chart down here is showing how you can move back and forth between solubility and KSP. If we knew the mass solubility of our compound, how many grams will dissolve in a liter, we could then convert that into the molar solubility, or we would have the molarity, big M, molarity. And then you could take that and you could then use those values to calculate the concentrations of each of the ions, and from that you could get the KSP. In other words, you could get the numbers for the concentration of the barium and the concentration of the sulfate. And if you knew those two numbers, you could multiply them together and get the value for the KSP. Or if we were down here at the barium phosphate, you'd do the same thing, although you'd take the concentration of barium and you would cube it because it's got an exponent of 3. And you'd take the concentration of phosphate and you'd square it because you can see it's got an exponent of 2. That's actually not too difficult to do. It's going in the other direction that becomes difficult. Taking the KSP and calculating the molar concentration of the ions. So that's what we're going to be doing on this next slide. That's a harder thing to do. Let me see if sharing works, because I know that's a better way to do this. No, it just doesn't want to work. Well, I'm going to try one more thing here, guys, because it just would be easier for you to see it if I can do that. Nope, not a happening. Okay, I'll return to sharing my screen. So here is how you would calculate the solubility concentration of the ions from the KSP. Oops, that's not what I wanted. Okay, here we go. So they're saying here that the equilibrium constant for this compound, calcium fluoride, is 3.9 times 10 to the negative 11. Below that, we've got an equation for what would happen if for the calcium fluoride that does dissolve. Gives you 1 calcium cation, gives you 2 fluoride anions. Again, I was asking, where does the coefficient 2 come from? It comes from the subscript in the compound. We can then write out what's the formula look like for the equilibrium constant. Well, it's going to be the concentration of the calcium coming from the equation up here, and then the concentration of the fluoride. But remember, you take the 2 and you use that as the exponent on the fluoride. It was given that the KSP value is 3.9 times 10 to the negative 11, so that's why you're seeing it down here. Now we'd like to know what those values are. We're going to use a Rice table in order to do that. So you've got the calcium fluoride as the reactant, and you got the calcium 2+ and the fluoride as the products. Now, there's not going to be any value for the calcium fluoride because it's a solid. It does not have a concentration. It's meaningless to say that it has a concentration. Or you can say a concentration is 1. But anyway, we're just going to leave those blank. So we start out at the very beginning, which at the beginning, if we go to this picture, you just have your insoluble compound. And there are no ions yet. There's no little green ones floating around and gray ones floating around. So it's going to be 0 for both of those. Then we algebraically represent the change in the concentration going from our equation up here. You can see it's 1x for the calcium and it's 2x for the fluoride because you got a coefficient of 1 on the calcium and a coefficient of 2 on the fluoride. So that's why that's 1x and 2x. We apply the change to the starting concentrations that were 0, and it's still going to be 1x and 2x. Now we'll take that and put it into, we'll go ahead and simplify it. So up here, it was given that the KSP was 3.9 times 10 to the negative 11. And then the concentration of the calcium was X. The concentration of the fluoride was 2x. So we're going to square the 2x like we had here, or we had right here. We're going to square it. So we simplify that. Sorry, folks, for the noise there. So to simplify it, we've got x times x squared gives you x cubed. So x times x squared gives you x cubed. 2 squared gives you 4. We bring it down to here, and we're simplifying for x. Now, this is not showing you the intermediate steps. Those steps would be you take the cube root of the 3.9 times 10 to the negative 11 divided by 4. You need to move the 4 to the other side of the equality. So to move the 4 to the other side, you would divide it by 4. So now you got 3.9 times 10 to the negative 11 divided by 4, but you'd still have x cubed on the right side. So to take that from x cubed to x, you would have to take the cube root of both sides. So you're taking the cube root of 3.9 times 10 to the negative 11 divided by 4. Your result's 2.1 times 10 to the negative 4. But then once you know x, you have to be careful how you interpret it. X is the concentration of the calcium cation. So it is the 2.1 times 10 to the negative 4. But 2x is the concentration of the fluoride. Remember, if we go back to the table here, the concentration of the fluoride is 2x. This is why you want to do a Rice table, so you would know that that's 2x. So concentration of fluoride is 2x, so the concentration of the fluoride is 4.2 times 10 to the negative 4. And then if the question that's being asked is, what is the concentration of the calcium fluoride that dissolved? It's 2.1 times 10 to the negative 4, or it's equal to x. So just be careful how you interpret what x is actually representing. Okay? So has anybody got a question about what we did up to this point on the solubilities? Just give me a chat, please, if there is. In fact, I'm going to stop sharing this anyway. You're going to divide it by 4 and then take the cube root.